This is Mr. Baker, and we're going to go over the graphs review for the Algebra 2 end of course test. This follows the worksheet that we got a few days ago, and let's just go ahead and get to it. All right, for our first problem, which of these could be the equation for this graph? Now, no calculators on this problem, so we can't just plug all the equations in and look at the graphs. So we're going to have to analyze this, and there's going to be some features about this graph that we should be able to figure out and help us eliminate. One of those features is going to be the degree. So what's the degree of this equation? Now we can figure that out, if you remember, by just counting the number of directions it goes. This one goes down, up, down. So that's 3 different directions. It's degree 3. Well, if we know this is degree 3, we know that the biggest exponent in the equation should be the degree, or is going to be the degree. So we can already eliminate 2 answers. It's not going to be A or B, because neither one of those is degree 3. They're degree 2. But the other 2 are both degree 3 here, degree 3 here. And so how do we figure that out? Well, there's other stuff we can figure out. Probably the right end behavior. Now the right end behavior on this one goes down, and that translates to a certain part of the equation, and it's our A, it's our leading coefficient. So all we've got to do, we know that down means the A is going to be negative. Only one of these is like that, and that's D. So we know our answer has to be D on this graph. Negative x cubed plus x squared plus x. It's the only one that's degree 3 and has a negative leading coefficient. All right, so our next question, the graph of g of x is translated up 5 units to produce the graph of the function h of x. Which of the following could be h of x? What this is really going to ask us is, how do we shift a graph up? What is it we do? Well, g of x or h of x or f of x, any of those, it's just y. So y equals whatever. In this case, the y originally equaled x cubed minus 9x squared plus 3x minus 1. If we want to shift that up, well, that means we want to make the y value bigger. So whatever we got from plugging in x into our whatever gave us a y value. If we want to make that 5 bigger, we just add 5 to it, or however much we want to shift it up. Just adding it on to the end is going to make the y value that much bigger, and for every point, and it's going to move the whole graph up that many steps. We did that with vertex form, adding the vertical shift on the outside. We did that with sine and cosine equations when we had a midline shift up or down. So in this case, that's our starting equation. We want it to go up, so we're going to add 5 to that, and then just combine like terms to see what we're left with. Only like terms are right here. Negative 1 plus 5 is 4. None of the rest of it changes. Well, that looks like C to me, so that's our answer. Now, if we wanted this to shift down 2, we would subtract 2 at the end. If we wanted to shift it up 7, we'd add 7 at the end. But as long as it's shifting up or down, a translation up or down, then all you got to do is add or subtract some number to the end. Number 3, got 3 different functions here. Click the boxes within the table that describe the end behavior of each function as x goes to infinity. That's how we say that one. X goes to infinity. That's the first thing we've got to make sure we know what we're talking about. What does it mean for x to go to infinity? Well, we've talked about that as far as notation goes. We should know which side that is. X is going to positive infinity. That means x keeps getting bigger. That happens on the right side of an axis. So that means we're talking about our right end behavior. So the extreme right side as it goes off the screen, if we're thinking calculators. Well, what controls the right end behavior? We've already talked about that on the first problem. Right end behavior is controlled by that leading coefficient, that a value. So we can look at each one of these. Look at f of x there. Doesn't have a number, which means it's 1. 1 is positive, so what does that mean about that right end behavior? Well, positive means it's going to go up. And if it goes up, that means it's going to be increasing. As we go to the right, it goes up, so it's increasing in value. Well, how about g of x? Well, here we got -1 as our a. Well, a negative leading coefficient means that right end is going to go down. So g of x is going to be decreasing on that right side. H of x has a -2 leading coefficient, also decreasing. Going downhill, so decreasing there. Now, that's all the question was asking, but what if it asked about the left end behavior? Can we figure out the left end behavior as well? Well, we could. In addition to the leading coefficient and figuring out what the right side's doing, we'd then have to make sure we know about the degree. And if we look at those degree, because we know in an odd degree, degree 3, like f of x, whatever the right side does, the left side's going to do the opposite. So f of x, since the right side's increasing, the left side's going to be decreasing. The left side's going to go down. G of x, that's an even degree, degree 2. So again, if the right side's going down, even degrees do the same thing, so the left side would also be going down. H of x, it's an odd degree, right side goes down, so the left side's going to be going up. That's where that one would go. Now, that's not what the question was asking, but it could have. The end of course test could certainly ask a question like that. Neither one required a calculator, just to understand how the equations worked. All right, number 4. H of x is a polynomial of degree 3. As the value of x increases, the value of h of x decreases. As the value of x decreases, the value of h of x increases. Which polynomial function exhibits the same end behavior as h of x? Now, this is actually an easy problem that they've tried to make a little more complicated by making you compare functions that we don't necessarily see all of. Specifically, compare the end behavior of the functions. So what do we know about these functions? Let's focus on h of x for a minute. It's a polynomial of degree 3, which means typically it's going to look like one of these two things. Either it's going to go up, up, or it's going to go down, down. That's what degree 3 does. Now, it doesn't have to. A degree 3 could just wiggle on its way up instead of a full direction turn. But it doesn't really matter in this problem because it's only the ends we're thinking about. Whether it's the either one of those, we're talking about that left side or that right side end behavior. But none of these have degree 3 at all. Degree 4, degree 5, degree 4, degree 5. Those biggest exponents give it away. So we're not looking for that, but that's okay. It doesn't ask for us to have this degree 3. We're not looking for h of x. We're just looking for something with the same end behavior as h of x. Well, let's think about how end behavior works for different degrees, specifically whether the degrees are even or odd. And we've already talked about this in passing. This one focuses on a little bit more. We know that even degrees are going to have the same end behaviors. Either both sides go up or both sides go down. Whereas odd degrees, they're going to have different end behaviors. One side goes up, the other side goes down. Well, that's what we've got here is an odd degree. Not only is 3 odd, but we see one side goes up, one side goes down in either of our examples here. So if we want something with the same end behaviors, well, it's going to have to be another odd degree. Because if we came up with something with an even degree, it can't do the same things. Yeah, the right sides might do the same thing, but an even degree would also go up if the right side went up, and that's not what we're looking for. Well, if we know we need an odd degree, it's not one of the even degrees. Well, that leaves us with two things. They're both degree 5, which are both odd, One of them's got a positive coefficient, one of them's got a negative coefficient. So those are both things that dictate right-hand behavior. So we just got to figure out what the right-hand behavior of our degree 3 is. Well, we can do that because it tells us about it. It doesn't tell us what h of x is, but it tells us some stuff about it. Specifically, the second sentence says, as the value of value of x increases, the value of h of x decreases. Well, if x increases, what does that mean? Well, that means x is getting bigger. Since x moves left to right, bigger x values are on the right side, so that means we're talking about the right-end behavior. Well, on the right side, the value of h of x decreases. Now, of course, h of x is just talking about y. It's saying y value decreases. Well, as y values decrease, that means it's going down. So this is just really a fancy way of saying the right side goes down. Well, one of these is like that. This one's got a right side that goes down. And if the right side goes down, what does that say about our leading coefficient? Well, it's got to be negative. That first number dictates the right end, the last thing that the graph does. Well, the only one of these that does that, A or C, well, A doesn't do it. It's C that has a negative leading coefficient. So it's got to be C. Number 5, what values of x satisfies the system here? And we've got this system. Fortunately, we didn't have a note here saying that it's no calculator, so we can use a calculator on this, and that's probably what I would do. Now, there's a lot of ways to do it, and watching you guys do the worksheets, I saw an awful lot of people taking the x values, plugging them in for x, and it's a good thing to do. What's our goal then? Well, we want them to have the same y value. And if that's how you did this problem, that's going to work out great. It's not going to happen for A, it's not going to happen for B, it's not going to happen for C. Process of elimination gets you to D, but I would, of course, plug that one in as well. And plugging it on the calculator should be a pretty quick thing to do. But it's still not the quickest. It's not how I did this problem. I got the calculator out and did some graphing. Y1 equals the first equation, Y2 equals the second equation, and my graph's going to look something like that. Well, my answers are just going to come from the places these cross. And there's 2 places they cross. Honestly, we can eyeball this one pretty well. We can see it's nowhere on the negative axis, so it's not A, it's not B. 0, well, 0 is the y-axis, and they don't cross there, so it's pretty clearly D. Well, when we're taking an actual end-of-course test, there's no guarantee that it's going to be that obvious. So what if I do need to be a little more specific? The calculator will let you do that. Now, we could always trace it, but again, we've seen over and over again that tracing is not very exact. If I needed a little more exact, we hit second, trace, which gives us that calc concept, and then the 5th thing on that list is going to be intersect. So second, calc, intersect, and then it's going to ask you first curve, second curve. It should pick those automatically. Just enter, enter. Then it's going to ask you for a guess. If you're going to take a guess, just remember that the answer it gives you is going to be have the x value closest to your guess. So you don't have to take a guess, but then it'll always be pretty automatic. I usually type in a number to guess to make sure I get the answer I'm looking for. But that's all there is to this one. Just graph it, find where they cross. Anytime you're working with a system of equations with x and y, that's going to work out. Regardless of how you got there, the answer's got to be D. Number 6. There's only 7, so we're almost there. But between you and me, I am not a fan of this problem. Which function has a minimum value less than the minimum value of g of x? Now, I'm going to leave this video up. Who knows how many people are going to find it. If you find a better way to do this without resorting to calculus, please let me know. I can't think of anything but graphing them and comparing them. Now we do see that the minimum value for this function, the one that we're given, g of x, is -3. So let's just graph them and see which one has a minimum less than -3. Well, easier said than done. We take our calculator, we can graph the first one, and it looks like that. Now, here's my minimum. My absolute minimum is one of my relative minimum. And it looks like it's right about 3. Is it lower than 3? I don't know. There's only one way to find out. But right now I'm just going to record that as a maybe. Maybe something's going to be a little more obvious. B, well, B is definitely not it. This one bottoms out right around -1. So no, that one's not it. C, here's our graph for C. That one bottoms out. It's pretty close to -3. It looks like it might be a little bit higher than -3. Again, I'm not sure. I'm going to chart that as a maybe. A was maybe a little more convincing than C. D, we can rule D out pretty quickly as well. It only goes to -1. So I'm down to 50-50. 50-50 is not bad, but I'd like to do better. I'd like 100% chance of getting this right. So what can I do? Well, we could plug some numbers in or something, but as long as we're graphing, might as well just zoom in a little bit. The other thing I did, I've also graphed y equals -3, since that was our negative on the original graph. But when we look at that, it only barely pokes down below it right here. But does it go past it? Yes. It's got a minimum less, very, very slightly less than g of x's. So A is going to be my answer. We could zoom in on C as well, and it's not going to. But in general, my opinion of this one, not very good. There's probably a lot of ways we could have written an equation, to put in this mix that did a better job, or maybe asked about a relative minimum versus an absolute minimum. A lot of ways we could rewrite this problem better. But hey, whenever it's asking about maximums and minimums, it takes calculus to pinpoint those with a whole lot of accuracy, or a graphing calculator, so that's a graphing calculator problem. But we've moved on to number 7 at this point. I'm talking slower than I'm clicking. Which model best fits the data in each table below? So this is me kind of cheating. I put 2 questions here on number 7, but neither one takes a real long time. We've learned a couple ways to do this. One way would be to use the first, second, and third differences. Finite differences, I think, was the title we gave that, which is just figuring out how do we get from 3 to -2, from -2 to -4, from -4 to -3, and subtract each of those. If they're all the same, that means that I'm looking for a degree 1 equation, which means it would be linear. If they're not all the same, I'd do it again from those numbers and do that, and that would give me a quadratic if those are all the same. The third time they all give me the same, it's cubic. And exponential is a little bit special. The way exponential would work is each time you subtract, you get pretty much the same values back. And I say pretty much because if it's perfect, it's going to be exactly the same values. It'll just have shifted the y values over a little bit. But it's not a guarantee when you're using real world numbers, which scatter plots often do. So you're not guaranteed to get everything exactly the same. And I don't like those lack of guarantees. So I'd rather just put these into the table. And that's another thing that we've done. Put the x values in L1, the y values in L2. So that's stat, edit, and then start typing them right in. And then we can graph it and look at it. Maybe zoom stat, I think that's zoom 9, to get a good view of it. And this is what our points are going to look like. It's got this kind of J shape to it. Now a J, we don't have anything that we automatically get as a J shape, but it doesn't take much imagination to extend it over here and make more of a U shape. And that sounds a little more familiar, like a parabola. And parabolas are quadratics. So that one's definitely going to be quadratic. And this one, the numbers were perfect, so it would work if you did the first, second, and third differences, or you did the graph. Any way you look at it, we're talking quadratic. Now, I was less friendly with the exactness of the numbers in the second problem. So first, second, and third differences aren't going to give you exacts on this one because I found some exact numbers and then I added or subtracted a little bit to make them more like real world numbers. But still, when we graph them, we get a definite pattern to it. I think we're even missing 1, 2, 3. I don't think number 4 came on here. I'm not sure what the scale was I was using on these, but it doesn't need to all be there. We have a definite shape to it. It's not a U shape. Looks a little like the last one, but it flattens out over here, more like a water slide. Whee! But water slide, we talked about that one. Water slides are definitely exponential. What would a linear look like? Well, a linear would be a straight line or a big enough random cloud of stuff that you wouldn't be able to tell whether it was supposed to be something else. That's going to be linear. A cubic, either it's going to go up, maybe down, or look like a line with kind of a wiggle in the middle of it. That would be a cubic as well. We didn't have either one of those things happening. We had definite candidates for quadratic and exponential on these. And that's it for our graphs worksheet. It's one of the 5 worksheets we use to review. If you're watching this, right as I've assigned them, you know that I'm going to take these all together as a grade for a quiz grade on Tuesday. If you're watching these because you found them, I hope that you found these helpful for some different Algebra 2 graphs. And I hope you enjoyed it and hope you learned something.